6.023 into 10 to the power of 23. So basically, what the significance of this number is that 1 mole of a substance contains Avogadro number of particles. So for example, 1 mole of atoms means 6.023 into 10 to the power of 23 atoms. 1 mole of molecules means 6.023 into 10 to the power of 23 molecules. 1 mole of ions means 6.023 into 10 to the power of 23 ions. So as you can see over here, when I talk about the definition of a mole, now let's study this definition more closely. 1 mole of a substance is the amount that contains the same number of specific particles. So the reason I've written specific particles, it's because these can be atoms, these can be molecules, and these can be ions. So it can be anything. So same number of specific particles as the number of atoms in 12 grams of carbon 12. So 12 grams of carbon 12 is basically, as we will understand in the slides to come, when we will do mole calculations, we will understand that 12 grams of carbon 12 refers to 1 mole of carbon 12. So 1 mole of carbon 12 contains 6.023 into 10 to the power of 23 atoms, and that's why 1 mole of a substance is the amount that contains the same number of specific particles, which means the particles can be atoms, molecules, or ions, as the number of atoms in 12 grams of carbon 12, which means 1 mole of carbon 12, which means 6.023 into 10 to the power of 23 atoms. So that's what mole and Avogadro constant mean. So calculating AR using mass spectra. So we were talking about relative atomic mass. I have given you the definition here again. It's the same definition that I had written in the previous slide. But the reason I have written it over here as well is because we emphasize on what it actually means. So for example, we have chlorine, okay? Chlorine has two isotopes, which are Cl35 and Cl37. Now, both of these isotopes have different abundances in nature. The abundance of the chlorine 35 isotope is 75%, the percentage abundance, and the percentage abundance of the Cl37 isotope is 25%. So the definition of relative atomic mass says that it is the average mass of the atoms of the naturally occurring isotopes of an element relative to 1/12 the mass of a carbon 12 atom. So basically, we have to calculate the average mass of these two, keeping in mind their relative abundances in nature. So if I had to draw a graph, where this is the relative abundance, and in percentage, measured in percentage, and this is the mass to charge, or ME ratio. Now what the ME ratio is, you don't really need to know. We will be focusing more on ME ratio when we do A-level chemistry. There is a topic on mass spectrometry over there, and we will be doing that in A-level chemistry in our A2 level. But for now, we don't need to know what it means. We just need to know that ME ratio is the same as the molecular mass of these. So in the mass spectrum of chlorine, we will have two peaks because two isotopes, so two peaks. One will be this peak, and it will be 35 because the molecular mass of this peak is 35. The mass of this peak, not the molecular mass, but the mass of this peak is 35. And we have this peak, and we have 37 over here, and the mass corresponding to this is 37 because the mass of this isotope is 37, the isotopic mass. So the relative abundance over here is 75%, 75, and the relative abundance over here is 25. So to calculate the relative, so we have the isotopic masses of chlorine, we have the relative of the isotopes of chlorine, have the relative abundance of the isotopes of chlorine. So we have the isotopic masses of the isotopes of chlorine, and we have the relative abundances of the isotopes of chlorine. So AR will be equal to 35 into 75, which is basically the mass into the percentage abundance. 35 into 75 plus 37 into 25, again the mass into the percentage abundance, over 100, because if you see 75 plus 25 is 100, so over 100, because over a scale of 100% we have 35 into 75 plus 37 into 25. So when we calculate this, when I do this on my calculator, I get 35 into 75 plus 37 into 25 divided by 100. So I get 35.5. And that's why the atomic mass, the relative atomic mass of chlorine is 35.5. So the relative atomic mass of a chlorine atom, which is the average mass of the atoms of the naturally occurring isotopes. So we have the naturally occurring isotopes of chlorine and the relative abundances. We have their average mass, which is 35.5, and this is relative to 1 by 12th the mass of a carbon 12 atom, because it's relative to 1, because 1 by 12th of the mass of a carbon 12 atom is 1. So relative to 1, so 35.5 over 1 is the same as 35.5. So this is the relative atomic mass of chlorine, and that's how we calculate relative atomic masses. Now we are going to do some exercises wherein we will be calculating the relative atomic masses of some elements. So a naturally occurring sample of cerium contains only 4 isotopes. Data for 3 of the isotopes are shown in the table. So for Ce-136, the relative isotopic mass is this 135.907. For Ce-138, it is this. For Ce-140, it is this. And for Ce-142, we have to calculate it. So this is what we need to get. And then again, the percentage abundance for this one is this. Similarly for this one. Similarly for this one. And again, we have to calculate this. So we don't know the percentage abundance, we don't know the relative isotopic mass, and we are given the AR of the sample. So we are given the AR and we need to calculate the percentage abundance and the isotopic mass of Ce-142. So firstly, it is easy to calculate the percentage abundance because we know that the percentages of all the relative percentages of the percentage abundances of all 4 isotopes when added together will be equal to 100. So when all of these are added together, they will be equal to 100. So I can calculate the percentage abundance of Ce-142 by subtracting these 3 from 100. So 100 minus 0.185 plus 0.251 plus 88.450. Okay, so when I subtract this, what I get is, let me use my calculator, 0.185 plus 0.251 plus 88.450, I get 88.886, and 100 minus answer gives me 11.114. So this is the percentage abundance of Ce-142. Now let's apply the formula of AR. We know that AR, so first we will multiply 135.907 with its percentage abundance 0.185 plus, so we have multiplied these two together, then we will multiply these two together, plus 137.906 into 0.251. We have multiplied these together. Now we will multiply these two together, so it will be plus 139.905 times 88.450. 88.450 plus we have to multiply these two together, so we don't know the mass, so let's take the mass as x, and we know the percentage abundance, so it will be x into 11.114, and all this divided by 100, because all percentages add up to 100, will give me let's not write it here, let's just write it here, will give me the atomic mass, relative atomic mass. So they've already given me the relative atomic mass, 140.116, and I have to calculate the relative isotopic mass to 3 decimal places. They have specifically said 3 decimal places, so I will give my answer to 3 decimal places. So when you can use your calculators and calculate this, but when I use my calculator to calculate x, just a second, when I use my calculator to calculate x, then I get 141.915. So this is the isotopic mass, correct to 3 decimal places. So the relative isotopic mass of Ce-142 we have calculated as 141.915. This is how it's done. Let's do another question. So a sample of sulfur contains only 2 isotopes. Sulfur 32, which has an isotopic mass of 32.0, and sulfur 34, which has an isotopic mass of 34.0. The relative atomic mass of the sample is 32.09. So when we calculate the average masses using their percentage abundances, we get 32.09. Calculate the percentage abundance of the isotopes present in the sample. So we don't know the percentage abundances, so we can take this as x, and we know that there are only 2 isotopes. So the percentage abundance of this isotope will be 100 minus x, because it has to add up to 100. So x plus 100 minus x adds up to 100. So this means that 32 times x plus 34 times 100 minus x over 100, because the 2 percentages add up to 100, is equal to 32.09, which is the relative atomic mass. So when I calculate x using my calculator, I get x. You can do it, you can pause the video and calculate on your own, but I'm just fast forwarding this to x is equal to 95.5%. I get x is equal to 95.5%, and hence 100 minus x will be 4.5%. 4.5%. So the percentage abundance of sulfur 32, which was x, is 95.5%. And the percentage abundance of sulfur 34, which was 100 minus x%, will be 4.5%. So we have got the 2 percentage abundances. These two add up to 100.